Alright guys, you're welcome to the next tutorial on the object detection through computer vision important terms. Today we shall be looking at cross-entropy loss. Cross-entropy loss is one of the forms of loss function or objective function that you often see in most algorithms in computer vision and in some other application domain. Now, what essentially the high level of this objective function is to be able to train our model accurately to be able to predict the labels or what you call the ground truth correctly. Now, during training of our models, essentially what you're trying to do is to learn a certain set of numbers, which we call the weights and the biases, often referred to as the parameters of the network. And in order to be able to iteratively adjust these values of the parameters, we need a way to be able to measure how well our model or our network has learned. And in most supervised learning, you do this by providing a label or a ground truth to your network so that the network will be able to compare its answers with the labels, also referred to as comparing its prediction with the ground truth. So, and cross-entropy law helps to be able to measure how well or how bad is the prediction of the model compared to the ground truth. So, for instance, if you take an image classification where you are predicting one object class, so that's essentially a binary cross-entropy task. And the general format of the function is that it takes in two variables, P and Q, where in this case P is the true label and Q is the output of the model, which is the model prediction. And this is the equation of the function. It is pi log I sum over the number of training samples that we have, or the number of batches. So the P is our prediction and the Q is the P is our true labels and Q is our model prediction. So when we're dealing with a binary case, you know that our P or our Q can only fall between two values. That is, P can only take numbers from 1 and 0. Likewise, Q can only take number from 1 and 0. So we say that P can take numbers from Y and 1 minus Y, and Q can take number from the set Y hat and 1 minus Y hat. So model predictions can be referred to as y hat or 1 minus y hat. And so when we key in those set into this original equation here, so if the ground truth is y, we expect our model to predict y hat, and if the ground truth is 1 minus y, we expect our model to predict 1 minus y hat. So that's essentially what you're seeing here. So if we key in those into the formula, this results into this. Now when you have a number of training examples, say for instance n, you sum over this whole loss into the number of training examples and you normalize by n. Now what's happening here is this. Usually when you are training a model or training a network, you don't just use one example. You might want to use hundreds of thousands of examples, and that is what is referred to as the N. That is most time is referred to as the capital N. But out of this capital N, you may want to take a subset called M, which will be a subset of your capital N. So the M is referred to as your mini batch. So let's say you have 100 examples, for instance. You may want to take your M, the mini batch, as maybe 10, 10, 10, 10. So that means you have to go through 10 times for you to be able to go through the entire number of training samples, which is referred to as one epoch. So the number of iterations will be 10 in that situation for you to have one epoch. Now what's happening here is this. When you take your training batch, which is M, you compute the loss for each of the uh, training example in your M, and after you have computed all their losses, then you want to add up all the loss and divide them by M, that is average. So that's what this M is doing. You're trying to do average. For instance, your I starts from 1, you get the loss, the key in the values that is your ground truth here and the prediction here, and you key in all these values, you get your number. You take I is 2, you key in the value, you get your number. Take I is 3 up to I is 10 in our example, then you have 10 numbers that you have gotten by keying them into this equation. Then you add up all those numbers, then you divide by your M and do it negative. So that will give you the average. So once you have a single number, then it is that single number that you now use to update your network, that you use to propagate back the parameters of your network. So now, how does this happen, and how does we verify that this loss function is actually doing what we want it to do? One thing you should understand is that we have the answer by providing the ground truth, and we're trying to train our model to be as correct as to predict as close as possible to the ground truth. If the model we're training is able to predict all the ground truth correctly, then we have an ideal model. But most models will not be able to, but we want them to be as close as possible. So for instance, if the ground truth for a particular example in our training set is 1, y is 1, we expect our y hat, which is our model prediction, to also be 1. But if our y hat could not be 1, at least we expect our y hat to be something like from 0.7, 0.8, 0.9, thereabout, at least to be as close as possible to 1. So that's why if y is 1, if you substitute y equals to 1 in this place, you will discover that the entire of this right hand side will become 0, because by the time you put 1 here, this will become 0. And by the time you put 1 here, what will be left is just log of y hat, negative log of y hat, because of this negative. And when you have this negative log of y hat, now imagine that our model predicts the y hat to be equals to 1. Log of 1 will be 0. So this entire one will be 0. That means this loss function has been minimized to its barest minimum, because we want the loss function to be minimized. That is, the output of this loss to be as close as possible to 0. But let's say, for instance, that instead of our y hat predicting this one as 1, let's say it's now predicting it as 0.1, which is actually very far away from 1. So if we take, for instance, I'm doing that on my calculator, 0.1, and you take the log of 0.1, what you're going to get is log of 0.1 is going to give you negative 1. Negative 1 times 1 is going to give you 1, and this is very high. So the loss function is trying to what? To minimize that 1. To minimize that 1 and force it down to be as close as possible to 0. Okay. So similar thing happens here when, so essentially, so this requires a large y hat. That is, for the loss function, for this equation to be able to work in line, so y hat has to be as much as possible close to 1. So if it is 1, then we have what? 0, and this will be 0, which favors what the loss actually wants, that is to be minimal. Now when y is equal to 0, that is the ground truth, we expect that our model also predicts 0. So if, for instance, our model predicts 0, because by the time you substitute y equals to 0 in this place, the whole of this way is going to become 0. We are left with this side, and this is 0, so this become 1, so we are left with this. That is what we have here. So if you say negative log 1 minus y hat, if our y hat got it correct and it predicts 0, then log of 1 is 0 and negative 0 gives us 0, and that is what we want. We want y into y at y to be as much as possible close to 0. Remember, we always minimize our loss function. But let's say, for instance, that our y hat is very large and our y hat is now predicting 1, close to 1. Let's say it's predicting is 0.9. By the time you say 1 minus 0.9, you are going to get 0.1. And by the time you say the log of 0.1, I'm doing that on my calculator, 0.1 log is going to give you negative 1, and negative 1 multiplied by 1 is going to give you 1, and that is very high. Remember, I want our loss function to be as much as possible close to a 0, so that will be penalized. So that's essentially what's happened in binary cross entropy. Remember that when our model predicts some kind of continuous numbers. So you first of all pass this model output through a sigmoid function that will squash the output into 0 and 1 before you actually pass it through the TensorFlow implementation of the cross entropy laws. Thank you very much. Hopefully somebody has benefited from this, which you often see in most literatures that has to do with minimizing an objective function for most applications. Thank you. Do give us a like if you have benefited from this, and see you in the next one. Thank you.